Hello, my name is Luke Herrin. This will be my submission for Math 4160 final project. The prompt is asking me to calculate the infinite sum of 1 over n to the 6th using residue theorem and by following the examples laid out in page 142 of our textbook. So we're going to go ahead and jump right in. Given that example in the textbook, they used an f of z equal to pi of some g of z, in their case it was 1 over z squared, times cotangent pi z. Now in this case, the reason why I wrote it this way is I'd like to change the g of z to 1 over z to the 6th power because I'm calculating the sum of 1 over n to the 6th. And you'll see why that's really important in just a moment because we're going to go ahead and calculate the residues. Recall that cotangent of pi z equals cosine pi z over sine pi z. So therefore, for all integer values of z, sine of pi z will be 0. Thus we have some singularities there. So we're going to calculate the residue of f at n, and we're going to use that using the definition, limit as z approaches n of z minus n, and times the function. We split that up. This left side right here, we'll evaluate using L'Hopital's, which will give us pi of cosine pi z in the denominator, which cancels with that pi and that cosine, and then it evaluates to 1, and then the right side is left as limit as z approaches n of g of z, which just equals g of n for some n in z, or I should say for all in this case, because they will all give sine pi z equal to 0. So change that to all for all n in z not including 0. The reason we're not going to include 0 is because 0 also has another singularity at this g of z, which is inside f of z. So we're going to calculate that separately. We will do this by expanding f of z using the Laurent expansion of cotangent, and then we're going to multiply that expansion by pi over z to the 6th. And what that gives us is this guy right here. Thus, the residue of f at 0 is negative 2 pi to the 6th over 945, because that is the coefficient of z to the negative 1. All right, so we're going to go ahead and move on into bounding, understanding the bounds of our functions. So in 2, we want to see that the cotangent, the modulus of the cotangent is less than or equal to 2. So what we'll do is split that up once again, use the hyperbolic definitions of it, use the, which will result in this guy right here. Then what we'll do is use the triangle inequality and reverse triangle inequality to show that this denominator is less than or equal to 1 over the single term denominator of modulus of e to the negative 2 pi z. Thus, this expression is less than or equal to this guy, which is less than or equal to this guy right here. Because it's a single term denominator, we can distribute it across the top. And what that will give us is 1 plus 1 over e to the negative 2 pi z, making that exponent positive. That's a circle, so the modulus equals 1. Thus, this equals 2. And the modulus of cotangent pi z is less than or equal to 2. All right. So now we have down here, we want to show, using the ML theorem, a couple different things here. So by the ML theorem, we can say that the integral over gamma of f must be less than or equal to the length of gamma times the maximum of our function. The length of gamma is simply the sum of all the sides of our rectangle. The max of this, well, recall, max of cotangent pi z is 2, so the numerator will just be 2 pi. The bottom right here is the maximum of the modulus of z to the 6th power for all z on gamma n. The modulus of z can only be a maximum of capital N, which is the vertical distance, right, of our rectangle. And then that's to the 6th power. And then we just have our constants as well. So the limit as capital N approaches infinity of this integral will be bounded by the ML theorem right here. So thus we take the limit of the ML theorem as n approaches infinity, and we would get 0 due to our capital N in the denominator. All right, this is where it really gets interesting. So now we're going to bring together all these concepts. So real quick, let's just note that by the residue theorem, we can state that this integral of our function is equal to 2 pi I times the sum of the residues. So recall our residues for f at n, where n isn't 0 and n is an integer, equals g of n. And recall that this is for all n. So we have to say that this is for the sum of 1 over n to the 6th, which is g of n. And then what's this bounded by? It's bounded by little n, modulus of little n, less than capital N, right? The modulus of capital N, because of this circle right here. So little n cannot expand outside of our gamma, all right? All right, so then we have the residue at 0, of course, so this equals 2 pi I times the sum of that. Now we're going to take the limit. This is where it gets interesting. You'll recall that the limit of our integral is bounded by 0, so we can set the right-hand side of the residue theorem equal to 0. Thus, the 2 pi I goes away. Now recall, we're also taking the limit as n approaches infinity. Thus, this sum right here that we found up here in the residue implies that the modulus of n must be less than or equal to infinity. All right, so now that's going to go for n and negative n. So we need to split this sum into the sum of 1 over n to the 6, which is the positive side, from n equals 1 to infinity, right? And then the negative n's from 1 to infinity. But since the negative n's are to an even exponent, the negative can actually be canceled. These two are equal, and thus we can write them as the sum of each other. Divide off those 2's, move the now pi over 6 to the 945 to the left side, and then we get the sum of 1 over n to the 6 for n greater than or equal to 1 equals pi 6 over 945. Thank you guys so much for watching. I appreciate your patience, and let me know if there's anything in this proof that I could have done better. I appreciate your time. Thank you so much.